Hey there, folks. I was trying to get the sun out of my eyes here. Sorry. Well, we made it to chapter 23, the last chapter in the book. And again, I've told you several times this is kind of the most important chapter because it sort of leads us, where do we go from here, sort of thing. So it's about climate change, it's about change in the Earth system. So let's jump right into chapter 23 and talk about kind of all the things we've looked at this point and go back to really the beginning where we began to talk about the earth as a system. And so if the earth is a system, right, we know about systems. They're large complex machines or organisms that are made up of a lot of little parts. Well, then the question becomes, if you start tinkering with the parts, if you change this thing and move that thing, the system gets affected in big ways. So that's kind of what we're looking at here is how has the system been changed, and what does that mean, and how can we make things right, I guess, is the biggest point that they're making here. So that's kind of what we're talking about when they talk about system. And when we talk about change in the system, we're talking about global change. In other words, for a long time, we think of change, and we've kind of got this nationalistic thought, right? That we are a nation or we are a state or whatever, and so we kind of think on a local level. But more and more, we're having to now think on international level. In other words, the things that we do here in the United States um, can affect things all over the world. So really, we have to think on a global level and not just a local level anymore. So again, let's think about the Earth as a system. We have the atmosphere, we have the geosphere, we have the biosphere, and we have the hydrosphere. All those different parts, those big kind of parts, work together, kind of like a car, right? You've got the engine, and the engine's got a bunch of little parts. You've got the drive system, right, with the wheels and all that sort of thing. Then you got all the computer and instrumentation. So you got all these little sections of pieces that have pieces in and of themselves that are all part of the big system. And so those were the four big parts that we identified before in the Earth system, and kind of looked at them in those respects. So here's the Earth as a system. Now, what happens if you change some of these things? What happens if you change the atmosphere? What happens if you mess around with the hydrosphere? What happens if we change something in the biosphere, right? How does it affect the rest of the system? And that's kind of what scientists have been looking at and studying for quite some time. And we've come up with some pretty amazing things that have happened. So when we talk about change, we're looking at really two different kinds of changes. Let's look at unidirectional change. So whenever you see the word uni, right, or uni, you think of one or one thing. Like um, so, this is one directional change. In other words, if think of it this way: if I bake a cake, right, and I get the flour and I get the sugar and all those things, and I mix them together and I bake it, right, a chemical reaction has happened, and now I get a cake. I can't now take that cake and turn it back into all those um, different parts. In other words, I can't take the cake and get my flour back, right? Whereas if I took some dirt and some water and made some mud, right, then eventually I could get the water back out and I could get the dirt away from the water and kind of get back to my original component. So we're talking about unidirectional changes, things that happen one time and don't ever happen again. So your book goes into some of those, and we've already looked at quite a few of those, like, for example, the formation of the Earth. The Earth was formed 4.6 billion years ago. It was formed from planetesimals that came together and smashed together and eventually congealed into a large semi-spherical ball, right? But it will never go back to those planetesimals. It is now totally different. It will die a very different kind of death. So it is not anything that's going to happen over time again. It's a unidirectional change. For example, the evolution of the atmosphere, how we talked about the atmosphere started out with gases mainly from volcanic activity, sulfur dioxides, carbon dioxides, things like that. And now the atmosphere is totally different. Now there's nitrogen in the atmosphere and oxygen. and the atmosphere probably will not go back to the way it was before, or the oceans, or even the evolution of life is a unidirectional change. Life began as simple single cellular organisms and has changed and evolved into multicellular complex organisms like ourselves. And so it is not likely or even possible at this point that things would revert back. So these are unidirectional changes, things that happened kind of in one direction, and you're not able to kind of get back to where you were. That's opposed to cyclic changes. So we see a lot of this in nature, don't we? We see a lot of cycles. Um, Seasons are cycles, right? If we have a bad winter this winter, we can look forward to the next winter because it might be a little bit better. So that's a kind of cyclical change. We've seen cyclical change in the supercontinent cycle, where we get these supercontinents like Pangea. They break up, they become smaller continents. So we're in kind of in a breakup period. But sometime in the future, all the continents will form back together into a supercontinent. We're pretty clear on that. And unfortunately, we won't be around to see it, but it is a kind of cyclical change that we see. Other kinds of cyclical changes, like the weather and like climate. We're going to talk about climate here in a little bit, but climate is a good example because we've had warm periods, we've had cold periods. So the climate can go back and forth. During the period of the dinosaurs, here you can see a little diagram here of these sea level changes. Well, right here is the bulk of the dinosaurs. This is where the dinosaurs were most influential, and this is that warming period. And because it was so warm, all the ice was melted, so there was lots of water to fill in the oceans. But then, as the dinosaurs are gone, now the Earth is cooled. That cooling has caused more ice to form in the Arctic, and so that ice leaves the ocean and becomes locked up in ice. And so now we're beginning to look at another warming period, aren't we? That we see in our future, and that's one of the things we'll talk about. So when we argue, you can look at this right here, and you can argue, well, we're almost getting back to normal. This is 0 meters. We're almost getting back to sort of a normal state. That's true. And notice where we could be, right? We could be gone with ice and have all this water. But remember, this was a time during the continental divergence. So it was one giant supercontinent here, wasn't there? And so the water level wasn't that big of a deal. Now, if you've got the land spread out over a larger area and you add all this water, you're going to lose quite a bit of land. I mean, can you imagine? Most of the people living in the United States live near the ocean. Cities like New York, cities like uh, um, Miami, all these Boston, all these large cities that are near the ocean, they're going to be gone if sea levels were at this level, 200 plus meters higher than normal. So it is kind of a big deal, even though people say, well, it was that way in the past. Well, that's true, but we weren't here. We didn't have all this investment in the land. So yeah, the Earth is going to survive, but it's going to look like a very different place. Some other cyclic cycles, the rock cycle is a good example. The hydrologic cycle, the water cycle, right? The carbon cycle. So all these cycles that we've studied since you were in third grade are part of this cyclical change as well. So cyclical changes come and go, right? And it just kind of depends on where you are in the process as to whether or not it's a good thing or a bad thing. Now, let's look at climate for a minute. Let's look at climate change for a minute. Again, we said climate always changes. Things are getting warmer, things are getting hotter, things are getting wetter, things are getting drier. All these things have happened to the Earth in great extreme in the past. And so some people can argue, well, so it's going to get warm, so what? So one of the things we have to understand is when we talk about global climate change, we are talking about the Earth changing, but really, in fact, we're talking about that change happening during a period of modern humans, right? We're talking about this happening at a time when modern humans are here. We've built cities. We've done all this stuff to the planet, and so this is going to be a different. This is going to be a different thing than when it happened during the period of the dinosaurs. This is going to be very different. And so that's really what we're looking at when we're talking about saving the planet, or saving animals and species and that sort of thing. That's true, but really it has more to do with us and how are we going to save ourselves, right, as a species, as human beings. Um, we'll get into this in a minute, but really things have gone past the point of no return at this point. It is going to be a very different world for our children, and definitely for our children's children. And we'll see how that plays out. But global climate change is a real thing. In other words, we talked about this, I mentioned this before. Things we do on a local level are no longer local anymore. I mean, if you build a big power plant that's burning coal and putting carbon in the air, that carbon doesn't stay over your power plant. It goes all over the world and affects temperatures and climate all over the world. So it is a big deal. And um, we talk about this in terms of global warming, and we talk about this in terms of the greenhouse effect. Now, you've probably heard about this before, and I know you've probably studied this in third grade. I know you studied it in middle school. So, what is the greenhouse effect? How does the greenhouse effect actually work? And what are we talking about when we talk about greenhouse gases? Well, let's get to the greenhouse effect, right? Um, Most of us probably know what a greenhouse is. A greenhouse is a place where we grow plants when the temperature outside is cooler, because the greenhouse gets warm, not necessarily by added heat, but by the sun. It happens because if you can imagine the Earth as being a greenhouse, we use plates of glass or plastic, and what that does is it basically insulates the inside of the greenhouse. So radiation from the sun can go right through the glass, right? The light and the radiation goes right through the greenhouse, and you can stand inside a greenhouse, and when the sun's out, you can feel the sun on you, and you can feel that heat. So you know that this radiation passes right through uh, the glass or the plastic, right? And it begins to hit objects in the greenhouse. It hits the greenhouse floor, it hits the plants in the greenhouse. It hits the terracotta pots in the greenhouse. It hits the people working in the greenhouse. All these things get hit by this type of radiation from the sun. And then what happens to them, of course, is that heats up their molecules, which then radiate out and heat up the air inside the greenhouse, which is now trapped, isn't it? That hot air now cannot get out, can it? Because of the glass. So the radiation comes in a wavelength, in a form that can pass through the glass, but then it's converted into a form of energy that now is trapped in the air molecules and in the parts of the greenhouse that now it can't get out. So you're adding more and more energy, and more it heats up and heats up and heats up. And so now that heat is trapped. Well, this is what's happening on the Earth. The Earth can act like a greenhouse. And this atmosphere, right, that we've studied, certain gases that we call greenhouse gases act like that glass. In other words, in a normal situation where you just have nitrogen and oxygen basically in the atmosphere, then those molecules are small enough that that heat can radiate right out into space. But when we start getting bigger molecules, more complex carbon molecules, like carbon dioxide, like methane, then they are large enough that they begin to trap this heat energy, gets absorbed into those molecules and can't go out into space anymore, can it? And so now, just like in a greenhouse, these things are beginning to heat up. And as we add more and more of those molecules into the atmosphere, it's like thickening the glass. That now more and more heat energy is coming in, but now less and less can get out. And so the Earth begins to warm up. And that's the greenhouse effect. And so your book talks about, again, some of these molecules. And I just mentioned sort of the biggies. There's quite a few molecules that can do this, even water. But carbon dioxide and methane are two of the biggest because they are two of the ones that are created in the most abundant amounts. So carbon dioxide, we know, happens through just us breathing, doesn't it? So we are big creators of carbon dioxide gas. CH4, methane, can be created in lots of different ways, from car exhaust all the way to, again, us as humans having flatulence. That gas that comes out, that smell that comes out, is methane. And there's been some argument that having so many cows around is a problem because of their creation of methane. And so this whole thing acts as sort of a feedback mechanism. In other words, as more carbon dioxide is released, more and more energy is trapped. As more and more energy gets trapped, more and more carbon dioxide gets released, and the whole thing kind of continues. Um, it's most pronounced in the Arctic regions, if you think about it, because the Arctic regions have snow, and that white snow acts as a big mirror and reflects heat. But as more heat comes in and the snow and the ice melt, now we have a dark ocean, and that dark ocean is going to absorb heat. So it is sort of a kind of feedback loop in that the more energy we put in, the more energy we trap, and therefore the more energy gets put in again, which means more energy gets trapped, and the whole thing kind of goes to the point of absurdity, to where you wonder if it can be changed at all. Uh, Now, how do we study climate change? Well, there's lots of ways. Your book lists a whole different way. So this is a theory. This is an idea. This has been around for a long, long time. I mean, this is I can uh, this folks have been talking about this throughout the 20th century, and there was a lot of study done in the 1960s. The problem, of course, is right that this has become political. The problem, of course, is that we burn fossil fuels. That's how we get our energy. And there's a big industry around fossil fuels. There's a lot of money involved. And we've set up our entire economy. We've set up all of our machines, our cars, our businesses. Everything is designed to burn fossil fuel. And so we don't want to get away from that. It's going to be expensive if we try to shift to something different. That's the big argument, of course. So it has become political. But the truth of the matter is that it's not sustainable. Here you can see where we're beginning. So I guess my argument was that we people are trying to argue about clean coal and things like this. They don't exist. It's just all not. It's not sustainable. It cannot continue. Right? We're going to have to stop burning coal. We're going to have to stop using gasoline. We're going to have to look for alternatives. And if you come back to this planet 100 years from now, if you were given that opportunity, you would see that those predictions are true. They will not be using gasoline. They will not be using coal. They will not be using natural gas. They will have created new ways, solar energy, wind energy, all that sort of thing. That will be obvious. And if you talk to someone 100 years from now, they would just shake their head and just couldn't believe that you would use something so dirty and so disgusting to create energy. There's so much more efficient ways of doing it. But anyway, I keep getting off the track, and I apologize. But let's talk about how do we know what we know? What have we been doing, and what have we been studying? And your book lists all kinds of ways in which we've been looking at um, uh, evidence from stratospheric record in sedimentary strata, all the way down to the ice bubbles in ice. We can analyze the atmosphere in those, growth rings in trees, all these sorts of things uh, can lead us to the same conclusions. And again, we've been doing this at least since the 1960s and before that. So studying, learning that in fact these greenhouse gases have been building up, and they've been building up since the Industrial Revolution, right? I mean, before the 1720s, when and coal engines, and they began burning coal to create to run the looms, to run steam engines and all that sort of thing. Before that, things were somewhat under control. Right, the worst you could do was build a fire with wood, and but with the Industrial Revolution, things really took off. There's all kinds of stories about cities like London that everybody used coal for everything, and it'd be the middle of the day and it would be so dark you couldn't see where you were going because there was so much smoke. Um, we have a little region here in Louisville called Smoketown. And one of the reasons it's called Smoketown is because of the kilns that were in the area making brick. There was so much smoke and so much dust and gas, and it was just a nasty place to live. But it was so smoky you didn't go there. It was called Smoketown. So this has been going on for quite some time. It's gotten a little better from the standpoint of the amount, but again, as we're going to look at too, part of the problem is population, right? Back in the 1720s, there weren't very many people on the planet, but now we're in the billions and approaching tens of billions. So population is also a big problem. Not to mention the fact that a lot of the folks that have a high population suddenly um, they're wanting things that we have. In other words, I remember when you saw pictures of China used to be. If you saw a picture of Beijing, China, right? Look at old pictures from the 70s and 60s of China. There's thousands and thousands of bicycles and 4 or 5 cars. Look at pictures of China today. There's thousands and thousands of cars and 4 or 5 bicycles. And so they're wanting to progress just like everybody else. And so they've traded in their bicycles for cars, but that means pollution. That means burning more gasoline. That means more carbon in the air. So those sorts of things are all part of the difference in the change. Your book goes on to show you some of the work that scientists are doing. Now, this is important because it's important to understand that, again, getting back to this idea of theory, in science, a theory is a very important thing. It's not a guess, it's not just someone's hunch. When we talk about theories in science, we're talking about theories backed up by decades of research, decades of facts, decades of numbers and evidence, right? That go to form a theory. So people want to say, well, it's just somebody's theory. Well, that's not the way science works. You can use that word for other things, but in science, the word theory is incredibly powerful and is incredibly real. And so this theory is not anything that you can argue about. It exists, it's real, and it's something that the sooner we deal with it, the better off we're going to be. And we'll see how the politics is slowly changing. Hopefully, it will change soon enough, but we are definitely running out of time. Again, look at some of these really interesting charts about cooling and global temperatures over time. Again, you can almost trace where the dinosaurs had a very warm period. Here you can see these ice ages, and then we run into the Quaternary period where we have these cooling and these little ice ages. And the last one, of course, we've already discussed. It's about 12,000 years ago. But this, again, is a cyclic change. Locations of continents can cause changes. So here we can see 20 million years ago, before the Isthmus of Panama is formed, these cooling temperatures, so the water gets warmed here, and that warm water goes into the Pacific and can cause a change there. Now it's been blocked off, hasn't it? So now this warm water goes up into Europe. And so at this time, Europe is frozen. I mean, or Europe is, you couldn't live there if you wanted to. But now, with this closed off, this warmer water moves up into Europe. And so you can live in places like Italy and places like Great Britain, where it's actually quite a bit higher than Maine. But because of these climate changes, it's actually warmer and you're able to live there. Um, So these are kind of short term. We talk about short term changes, and those have happened on a fairly regular basis. Here we can see again. We've talked about these a little bit when we talk about ice ages, changes in Earth's orbit and tilt, changes in ocean currents, changes in eruptions of volcanic aerosols. All these things can cause changes, but we're getting down to the point where it is not something that is going to happen in terms of changes in climate, but changes from the standpoint of people. So some of these climatic events, again, can be kind of small, but some of them can be fairly large, and we've seen some of those already. For example, what we call these mass extinction events. So the last one we saw was with the dinosaurs. That was about 65 million years ago. And we've seen a lot of these before. There was a mass extinction event after the about 500 and so million years ago, right after the Cambrian explosion. We saw, so there's been several of these over time. Um, so your book begins to talk about then human impact on land and life, and I talked a little bit about this in some of the writing we did, uh, and that is that for the first time, an organism, humans, are able to change climate, um, change our environment. In other words, we've always believed that natural selection said that when environment changes, organisms change. Organisms either change the way they exist as an organism, or they go somewhere else, or they become extinct, right? Now, for the first time, though, we have an organism that can change its environment, and that's us. And so this is causing changes in the system, right, that we cannot predict. The Earth system is too complex. And so we're beginning to study and learn what some of these changes have evolved, and that's where climate change is coming from. We've talked about this already, the growth of population. So when I was born, the population of the Earth was about 3.5 to 4 billion. So I, in my lifetime, have seen the population over double, and so it's kind of amazing that for, as you can see here, for literally thousands of years, human population has been pretty steady, and then all of a sudden we get this exponential growth. And again, it's not just a question of more people, but also more people using more resources. And so that's been one of the biggest problems, is we don't have enough resources for all these people to use. And that's going to be an issue that we're going to have to deal with, because the population is going to continue to rise. Where it ends, we don't know. Now, pollution is something we've talked about, or at least dealt with, for a long time. And your book lists all kinds of the pollutions here, and there's quite a bit more. You could pretty much write an entire textbook on pollution. So, again, more people, more pollution, and more industrial waste, and the pollution becomes not just throwing paper on the ground, but becomes Superfund sites where, and even nuclear waste sites where places you can't even live there anymore. And so that's the kind of pollution that we're talking about. Um, Again, this idea of climate change has been happening for a long time, but now we're beginning to see the actual results of it, aren't we? We're beginning to see temperatures change. It may not snow very much here anymore. It We talked about the fact that 100 years ago they used to get ice off the Ohio River. That's people before they had refrigerators would go out and cut ice off the Ohio River. It will probably never freeze over anymore, at least not in our lifetime. We're now into the hurricane season for 2020, and we've seen more hurricanes this year and stronger hurricanes this year than ever before. And 9 of the hottest years have been of the last 10 years. So we're beginning to see what was been predicted for decades now. We're beginning to see these things happen. They're beginning to affect us. The sea levels are beginning to rise. There's places in Miami Beach that have to be closed during high tides because the water's coming up. And so, again, we don't know. This is like trying to turn the Titanic. It's going to take a long time. If we stopped using any fossil fuels ever again, just completely stopped right now, we're still looking at maybe 100 years before we could turn the Titanic and begin to see changes. So things have already been put into place that we're going to have to deal with. At least our kids and our kids' kids are going to have to deal with until they can get things kind of under control. And your book goes through here even more and more evidence of some of these problems, and that's what we're looking at here. Um, so, and again, there's lots of charts, lots of graphs. I know this is, if you can take the time to kind of walk through them, because they are very revealing, they are very interesting, and they are very telling. If you have any doubts at all about whether climate change is real, whether we should be rethinking um, how, as a world, we generate energy, then you really should take a look at this as closely as you can, because it will be quite revealing. Um, and again, I hate to end this on a downer note, but here's the good news, right? The good news is that we now know what the problem is. The science has worked very hard to make it very clear what the problem is. Now it's a question of human will as to whether or not we're going to make the changes that now we know we must do, right, in order to keep um, our way of life the way it is. Like I said, the planet's going to be fine. The planet's seen a lot worse than this. So the planet's going to be fine. It's not like we're saving the planet. What we do will save our kids and our kids' kids, right? It will may give them the same kind of life that we had. And so it can be a good thing. We will stop using fossil fuels. For one reason, they are non-renewable fuels, so they're going to go away at some point. And even if we tried to burn all of them, at some point we're going to run out. So we might as well be working on renewable energy now, and we are. Solar energy now is a lot cheaper than it's ever been, and the technology is there for wind energy and other kinds of renewable energy sources. So I think that is really our future. It's just a question of when will we decide that that's the direction we're going to go politically, and make that happen. So the Earth, as an Earth, what will happen to it? Well, we're about middle age. The sun will probably burn for about another 5 billion years. The Earth will probably last for another billion years or so before it uh, essentially the sun will be getting bigger and bigger and bigger. Um, Most of life on Earth will disappear within the next billion years or so, and the Earth will be pretty much inhabitable. Most of the water will evaporate away, and then eventually the sun will get so big that it will uh, encompass the Earth. Here is the sun as a red giant. There's the Earth's orbit. So the sun will get so big that will literally encompass the Earth, and so that will pretty much be the end of everything. But even in the universe, things are cyclical, aren't they? In other words, we have the carbon atoms, and we talked about this before. You're made of stardust. Um, in order for there to be the molecules to make you, there had to have been there had to have been a solar system, a star before that exploded and had created these elements for you to survive. So all this carbon, all this copper, all this iron, all this stuff will continue to go on long after the Earth is gone, long after the sun is gone, and maybe be a part of a whole other solar system. Who knows? But that's the end of chapter 23. Here are your review questions. If you want to look at them, and we'll see you next time.